Alright, so let's say you're given this diagram here of an electron traveling around a square path, and the question says, the force acting on an electron is equal to Fcxj, where C is a positive constant. The electron moves around in a square loop. Calculate the work done by the force over the electron's path. Is this force conservative? To start, our force equation is given here, where x is the displacement along the x-axis, j hat is the unit vector pointing along the y direction. And so if we look at this equation, we can note that the force is not constant. It depends on the position. And if we look at our diagram, the position changes throughout its motion along the x-axis. So we have to use the work equation for non-constant force given here, where dl is the small part of the path, F is the force, and F dot dl is also equal to F dl cos theta, where theta is the angle between the F and dl vector, and F dl are the magnitudes of the F vector and dl vector. We can apply this equation to the situation. So this is our diagram, and since the loop side lengths are L, we can label each vertice like so, and then we can define dl as a small segment along the path, so it travels in the counterclockwise direction. We can label dl like so. And then looking at F is always pointing in the y direction and increases with x. The force vector can be drawn like this. From here, we can split the integral into 4 path segments for each side, labeling 1, 2, 3, 4. So the total work is going to be equal to the work done for each path. We can start by finding the work associated with path 1, which is going to be given by this. We can rewrite it in this form, knowing that theta is the angle between them. And if we look at our diagram here, this is the force vector and this is dl. So the angle between them is going to be 90 degrees, and cos 90 is equal to 0. So if we plug that in, we get work 1 equal to 0. Since F is perpendicular to the change in the path dl, this is why we get force equal to 0. And work 3 is also equal to 0 since F is still perpendicular to dl for that path, as we can see in the diagram. Then we can continue by looking at work 2. And if we look at our diagram, the force and dl are pointing in the same direction. Theta is going to be equal to 0 in this case, and cos 0 is equal to 1. We get this equation here. So we can identify that P1 is going to be equal to L0, and then P2 is going to be equal to LL. But if we note, dl is only changing along the y direction, so we only need the y part of these vertices. So we're just going to need 0 and L. Then our force is going to be equal to Cx. And if we look at our diagram, our x value in this case is going to be equal to L. And lastly, we can change dl to dy since the path's along the y-axis, so we're only changing in the y. So we can plug all these values in, we get this expression here, and then we can take CL out of the integral since they don't depend on it, and then we can just compute the integral, and we get this final answer for work 2. And then we can finally do work 4, which is given by the same equation, and we can note that force is equal to C times x. In this case, for the fourth path, x is equal to 0, so the force is equal to 0 in this case. We can plug this in, and we get that the work done by the force along the path 4 is going to be equal to 0. So we can plug all these values in and find the total work. So this is the total work done on the electron by the force throughout its path. And since the starting and end point is the same for the electron, but the total work is not 0, this means that the force given in this question is not conservative.